All right, let's dive right into the super fascinating world of secret communication. We're going to unlock the very heart of how we all keep our digital lives private, and that's something called the cipher. I mean, who hasn't, right? We've all been there. And that basic fundamental desire for privacy, well, it's driven one of the most interesting fields in all of human history, cryptography. And today, we're going to pull back the curtain on its most important tool, the cipher.
So, here's what we've got on tap. First, we'll nail down what a cipher is. Then, we'll clear up that classic mix-up between ciphers and codes. After that, we'll take a quick trip back in time, check out the modern ciphers protecting us right now, and wrap up with the big one. What actually makes these things secure?
Okay, first things first. Before we can get into the really cool stuff, we've got to understand the basics, the building blocks. So let's get a really clear definition of what we're even talking about here. You know, at its core, a cipher isn't some kind of magic spell. It's just a recipe. Seriously, an algorithm is just a fancy word for a series of well-defined steps you follow to change something. It's a totally repeatable, logical procedure for scrambling a message, and then, of course, for unscrambling it. And here's some key lingo you'll need. Your original, totally readable message, that's called plain text. Simple enough. Now, once you run it through that cipher's recipe, you get ciphertext, and that's the scrambled, unreadable version that's actually safe to send out into the world. Okay, let's tackle something that trips up a ton of people. We throw the words code and cipher around like they're the same thing. But in the world of cryptography, nope, they are two very, very different things. And you can see the difference right here. A cipher, that works on the small stuff, individual letters or bits of data, using that repeatable process we talked about. A code, though, that's more like a secret dictionary. It takes whole words or even phrases, like attack at dawn, and swaps them out for a single code word, maybe something like eagle. You need a whole codebook to figure that out. So why do we use ciphers all the time today? Well, because codes are just not very practical anymore. I mean, can you imagine trying to protect a giant physical codebook? If the enemy gets their hands on that book, poof, your entire system is broken. Ciphers, on the other hand, are all about algorithms and keys, which makes them way more flexible, way more secure, and just a whole lot easier to manage in our digital world. All right, let's jump in our time machine and see how these ideas grew over the years. Because really, the story of ciphers is this constant, epic arms race between the people making the secrets and the people trying to break them. This timeline gives you a great bird's-eye view. We start way back with simple letter swapping in ancient Rome. Then things get a bit more complex in the Renaissance with something called polyalphabetic ciphers. Basically, think using a whole bunch of secret alphabets instead of just one. And then, bam, a massive leap forward with incredible machines like the Enigma, which sets the stage for the digital stuff we use today, like AES. So let's kick things off with one of the most famous examples from history. Picture it. Julius Caesar. He needs to send messages to his generals, but he can't risk the enemy reading them. His solution? It was actually pretty simple, but for its time, it was brilliant. And here's the magic behind it. The whole process is incredibly simple. All you do is pick a secret number. That's your key. Let's say our key is 3. Just like you see here, you shift every single letter in your message forward by that many places in the alphabet. So a G becomes a J, an O becomes an R, and so on. And you're left with unreadable ciphertext. To read it, your general on the other end just reverses the process, shifting every letter back by 3. Simple, right? So for centuries, ciphers got more and more clever. But the real game changer was when machines got involved. I'm talking about the famous German Enigma machine. This thing used a series of rotating disks to scramble the letters. And the crazy part is, the substitution changed with every single letter you typed. It created this constantly evolving, shifting cipher that was so complex it was thought to be literally unbreakable. And cracking it, well, that changed the course of World War II. And that brings us right up to today. Modern ciphers are basically the invisible locks that protect, well, everything. Your online banking, your private messages, top-level government secrets, you name it. The basic idea is still the same as Caesar's simple shift, but the complexity, oh, it's on a whole other planet. So in the modern world, we usually sort ciphers into 2 main buckets. The first is based on the type of key they use to lock and unlock the data. The second is based on how they chew through that data. And this difference right here is absolutely crucial. On one side, you have symmetric key algorithms, like that AES standard we mentioned. Think of it like this. The sender and the receiver use the exact same secret key. It's like you and a friend both having a copy of the same house key. Simple. But then you've got asymmetric systems, and this is where things get really clever. Here there are two keys, a public key you can give to anyone, and a private key that only you have. The public key is like an open padlock you can hand out. Anyone can snap it shut to lock a message for you, but only you with your unique private key can open it. This idea is the foundation of almost everything we do online securely, from shopping to sending private messages. The other way we categorize them is all about how they handle the data itself. Block ciphers are like a wood chipper. They take your data and chop it up into fixed-sized chunks, or blocks, and then encrypt each one. This is perfect for stuff that's just sitting there, like files on your hard drive. Then you have stream ciphers. These work more like a garden hose, encrypting a continuous flow of data one little bit at a time. This is what you want for things happening in real time, like a secure phone call or a streaming video. Okay, so this brings us to the million-dollar question, right? We have these incredibly powerful algorithms, these digital locks, but what is it that actually makes a modern cipher strong enough to stop a determined attacker in their tracks? Well, assuming the cipher's design itself is solid, its strength against what's called a brute force attack, that's where an attacker literally tries every single possible key, it all comes down to just two things. And here they are. First, you've got the attacker's raw computing power. How fast can their machine churn through guesses? But the second factor is way, way more important, and that's the key size. This is what determines the total number of possible keys an attacker would have to guess from. The father of information theory, a guy named Claude Shannon, actually proved this mathematically. He showed that for a cipher to be theoretically perfectly unbreakable, the key has to be totally random, at least as long as the message itself, and you can never, ever use it again. Now, that's not really practical for most things we do, so we do the next best thing. We just make the number of possible keys so ridiculously mind-bogglingly huge that guessing the right one becomes impossible. And this is where the sheer scale of it all just hits you. That number, 2 to the power of 256, that's a pretty standard number of possible keys for modern encryption. And that number isn't just big, it's beyond astronomical. We're talking more possible keys than there are atoms in the known universe. If you took every single computer on Earth and had them do nothing but guess keys, it would still take you billions upon billions of years to try them all. So breaking it by just guessing isn't just hard, it's what we call computationally infeasible. So that leaves us with a pretty heavy question, doesn't it? Our entire digital world, all of our secrets, our finances, our privacy, it's all built on the idea that these numbers are just too big to crack. But computing power keeps growing exponentially. And with brand new technologies like quantum computing on the horizon, technologies that could, in theory, make these kinds of problems trivial, what happens then? What happens when computationally infeasible isn't a guarantee anymore? What does that mean for the future of our privacy?